Next speaker is Abhijit Champanerkar, one of the organizers also, and he is going to talk about the geometric side as he has said.
So I thank the organizers for inviting me to speak,
Yourself?
and I also thank Rama and Tejas for taking care of many logistics for the conference for the workshop, and really getting such a tremendous response and getting all of the students. So I'm going to give us 3 lectures on hyperbolic knot theory. And we heard Elias speak about a revolution in knot theory caused by von Jones with the advent of the Jones polynomial. And around the 1980s, there was another revolution in in low dimensional topology, 3 manifolds, knot theory, knots and links, and so on, by Thurston. So this is about 1980s, and this was using the geometry. So many ideas kind of came forth, and the main sort of idea was that hyperbolic geometry is very useful to study 3 manifolds and knot theory. So hyperbolic geometry is used to study 3 manifolds, knots and links. So that's the theme. So I'm going to explore this. So in the first lecture, I will say something about some motivation behind this work, a little bit about hyperbolic, the hyperbolic plane and hyperbolic 3 space, and set up some things which we'll use later on. In the second lecture, we'll see more about hyperbolic 3 manifolds, some structure theorem for hyperbolic 3 manifolds, and how to build hyperbolic 3 manifolds. And in the third lecture, we'll see examples of hyperbolic knots and links. So that is the plan. In between one of the computational sessions, we'll also look at some computational programs like Snappy and Snap to compute hyperbolic and some geometric invariants. And this is this whole theory is very adaptable for computer implementation. So that will give you lots of tools for experimentation, as well as to just study and get build intuition. So the story starts where you have the basic idea of a geometry on a manifold, or geometric structure. So we have a geometry is a space. So a geometry X is a simply connected complete homogeneous Riemannian manifold. So homogeneous just means that any 2 points on the manifold, there is isometry carrying one point to the other. So at every point, the geometry looks the same. And you have a manifold, and this admits a geometric structure modeled on X. So if it admits a Riemannian metric, which is similar, complete and homogeneous, etc., and it's modeled on X, if you can find an atlas, if there exists an atlas such that all transition maps are isometries of X. And we want M to be complete and finite volume. So, what this means is you can see M in a couple of different ways. This also means that so this is equivalent to saying that you can have your pi 1 of M is acts on X by isometries, because X is simply connected. There is a covering space of M, and the covering space action is by isometries. The other way to also think about it is that your M is actually a quotient of X by some group of isometries. So, gamma is some discrete group of isometries of X, and it is acting freely and properly discontinuously and so on. So, I will just give an example, but what happens in dimension 2? So, dimension 2 is the best case scenario. We completely understand what happens here. You have the homogeneous geometries, which are your classical geometries. The homogeneous geometries here is your Euclidean geometry, the spherical geometry, and hyperbolic geometry. Now, these are, of course, Euclidean geometry is very classical, studied by Euclid, and then there is a long standing question about the Euclid's fifth postulate, and the resolution of Euclid's fifth postulate gives you the two different geometries. You get the spherical geometry in one way and the hyperbolic geometry in the other way. And so, although Euclidean geometry is very old, spherical and hyperbolic geometry are rather recent, especially hyperbolic geometry. So, about late 19th century. And what is an example of a geometric structure? The example of a geometric structure is say the torus. You have the torus here, and you can think of this as the Euclidean space quotiented by the group Z plus Z or Z2 acting by translations, independent translations. Note that when we draw this picture of the torus, this is not the geometric torus. It has points of negative curvature and whatnot. This is just a three-dimensional embedding. The torus over here, you will not be able to draw it in 3 space. You have to go to 4 space because it is S1 cross S1. So, so this picture is not really the Euclidean geometry, the flat torus. The Pacman torus, yes. So then you have to make it flat. Yeah. Another example is the projective plane. RP2, and this is equal. This again in the same idea. You have S2 quotiented by the cyclic group on 2 generators acting by the antipodal map. So, in dimensions 2 we have the homogeneous geometries, and we also know what the all 2 manifolds are. Yes, so does everyone know the classification of surfaces? So, the surfaces come in 2 types. The orientable ones and the non-orientable ones. So, you have orientable of genus G and these are, I will call this mg, and these are connected sum of tori of g tori. So, it looks like that, and if g is equal to 0, it is S2, and the non-orientable ones and these are the connected sum of GRP2s. And for the geometry, we have again a complete classification of the geometry. There are two manifolds, and they take a unique geometry, one of E2, S2 or H2. So, this is the uniformization theorem. Oh, I should mention, if g is equal to 0 here, this is S2. And so, the uniformization theorem says that you have a surface S has we should need some here. S is a closed surface then S has geometric structure modeled on one of E2, S2 or H2. Furthermore, you can completely classify which surface gets which structure. So, you have your Euler characteristic of the surface. So, if this is positive, you get S2, if this is equal to 0, you get E2, and if this is negative, you get H2. So, you can completely now classify the surfaces. You have RP2, you have a torus or the Klein bottle. So, this is Klein bottle and everything else. So, it is really a very nice picture, and the idea for which motivated Thurston's study was to see what happens for three dimensions. Also notice that in two-dimensional case, the most interesting geometry is the hyperbolic geometry, because most surfaces lie there. So, what happens for 3 dimensions? And so, here are the geometries, the homogeneous geometries. So, we have, like the 3 geometries in 2 dimensions, we have the 3 geometries in 3 dimensions. So, these are, in addition to being homogeneous, these are what are called also isotropic. Isotropic just means that at every point in every direction the space looks the same. So, not only are 2 points related by isometry, but the 2 points and if you pick any basis for the tangent space with the metric, you can also, it is transitive on that. So, you can take any point and a basis to any other point and a basis. It looks the same in all directions. Then the second thing are the anisotropic geometries, where you take the 2-dimensional picture and then add a third direction in terms of so of course, when you add a third dimension here, so these are the product geometries. If you take the product, you just get E3. So, these are the product geometries. And then in addition to the product geometries, you can also have a twisted product. So, the twisted product geometries, they are called nil and SL2, they really they are just names. What you are doing is you are effectively taking H2 cross E, but just twisting the action of how the metric works. And so, these are the twisted products. And there is also one more way you can take a twisted product depending on whether the base is 2 dimensional or 1 dimensional, and that is the last geometry which is solved. So, these are the 8 3 dimensional geometries. Now, I have arranged them in a certain way. So, and what, yes, the twisted product just is, if you take say for example H2 cross I, the metric is very straightforward. It is a metric for H2 in the first 2 coordinates and Euclidean metric in the third. The twisted product is the Euclidean. So, as you are far away in Euclidean thing, it will affect the metric over here. So, there is some interaction in the metric, and so when you do the interaction in the metric, this is when there is a model for it. You take the universal cover of PSL to R and put the metric and so on. It's well, when I write H2, there is always a metric. I am assuming a metric there. So, it is really R3 with some certain metric, with a different kind of metric. Yeah. And so, the big theorem in terms of geometry for 3 manifolds is that you can do something similar. You can have geometry for 3 manifolds. So, this is the geometrization of 3 manifolds, and this is a theorem which was conjectured by Thurston in the 80s and also proved by him for a big class of manifolds called Haken manifolds, and then proved by Perelman in full generality in 2003 using the Ricci flow, and that you do not need them to be Haken. So, what it says is that every closed 3 manifold has a natural decomposition along S2's tori or Klein bottles into pieces which are modeled on one of the 8 geometries. And so, the word natural here is important because the decomposition is so the decomposition along S2s is what is called the prime decomposition for 3 manifolds, and it is unique, and the decomposition along tori or Klein bottle is called the JSJ decomposition, and that is also canonical. So, what it means is that if you take some 3 manifold, there is only one way to cut it up, so that these each piece has this geometry based on these 8 geometries. And what is interesting about it is that among the 8 geometries, 7 of them can be explained using some surface geometry, and of course, it does not make it any simpler. It's well, it does make it little simpler, but you can understand some geometry of surfaces and some generalization of that, and try to see how it matches up. And so, these 7 are classified. So, 7 out of 8 are well understood in terms of of surface geometry. For if you know more about this, these are what are called Seifert fibered spaces, and you can classify them up to diffeomorphism, and then you can also understand the geometry which they take. And in addition, you need one more type of these are what are called torus semi bundles. Basically torus bundles. So, so the 7 of them are understood in terms of surfaces. So, the remaining one, and hence the most interesting one, is hyperbolic geometry. So, Thurston started studying hyperbolic geometry and how 3 manifolds can be given a hyperbolic structure, and how various deformations of hyperbolic structures come about, and so on. So, I am going to talk about in the later lectures about the hyperbolic structure on it, and then Kate will talk something about something related to the deformation of hyperbolic structures. So, yes. The manifolds with boundary have is a slightly simpler picture. They don't have 8 geometries. There are only 3 geometries which are involved for manifolds with boundary. And the other problem, well, it's not a problem. The fact is that there also need not be uniqueness. You could have 2 different geometries for manifolds. It's H3, it's SL2 tilde, and I think it's nil. Yes, no, sorry, Sol SL2 and H3. For knot complements, yes, I am going to talk about the geometrization of knot complements. For example, I will do that in the next lecture, but for example, torus knot complements have 2 different geometries. That is because you can see them as bundles over a surface as well as over S1. Hyperbolic knot complement is unique. The hyperbolic structure is unique. Yeah. The one word about now I have used closed surfaces everywhere and closed 3 manifolds. You can also have manifolds with boundary. You have to be careful. You need to have torus boundary for the geometrization. The other thing is, when you are thinking about geometry on manifolds with boundary, there is a completeness issue which comes in. So, the boundary cannot really be included in the geometry. So, whenever you have a manifold with boundary, the geometry which is involved is actually on the interior of the manifold, because otherwise, I mean, just simply if you just cut this off like this, you will just fall off. So, you cannot really have boundary when you have geometry. So, what you have to do, some kind of make this infinite in some way, but obviously there is an immediate problem because we need finite volume. So, we have to resolve that, and that will bring us to cusps, which we will talk about in the next talk. Any more questions? So, the second topic is, now let us understand a little bit about hyperbolic geometry, and I maybe tonight I will put up a list of references, and I also request the other speakers to if they can send a list of references and maybe some links or to the references, we can put them up on the website, so students can go and read up more things about read in details and fill in some details and look at some more examples and so on. So, the hyperbolic plane, as I said, you have the Euclid's 5th postulate. This is very classical, right? One of the versions of it is that if you are given if you're given a line and a point outside a line, there is a unique line passing through the point which is parallel to the given line. And for a long time, mathematicians were trying to deduce the fifth postulate from the other four postulates, thinking it was not independent. But it turned out that around, I think, maybe in the mid 19th century, they started getting geometries which satisfied the first four postulates, but not the fifth. And the way the fifth postulate resolves, meaning that there exists no line which is parallel to a given point outside a line, that gets you into S2. And if there are infinitely many lines which pass through a given point, that gets you to H2. So those are the two resolutions. And there's a wonderful way where you can see all of the three geometries in really one point of view, which is you look at R3 and you look at some quadratic forms on it, and you see the geometries appearing as the unit vectors in the quadratic form. So, for example, that is the standard S2 model you see, x1 squared plus x2 squared plus x3 squared equal to 1, and then you get S2, and the induced metric and everything, you can write down the isometries, and the great circles come in, intersection with planes, all of that very beautiful geometry also works for H2 if you take the hyperboloid model. So there is a very unified way, and you can also unify it more if you take Hamilton's quaternions and look at it from a quaternion point of view. So that also works out, and this was really very motivating. Hamilton's quaternions was very motivating to study hyperbolic geometry at the turn of 19th century, and so they really tried to extend quaternions in many different ways to fit hyperbolic geometry. So what is the model? So how do you really study a geometry? So we give a model, we just say that, okay, here is the space, here is the set of points, here is the metric, and then from the metric, once you give the metric, you can deduce what are the geodesics, what are the isometries, and so on. And there are many treatments in detail. But we do not, 3 years ago, we went through a whole detailed hyperbolic geometry workshop here. I think, was it in the same room? Yeah.
Yeah, this one.
So, and but we won't do that this time, because we won't get to hyperbolic three manifolds and hyperbolic knots. But I will put up references where these things are done in great detail. And the computations, the treatment is very nice, and it's actually also very accessible to undergraduates also. Not hyperbolic geometry, maybe a little bit later, but spherical geometry definitely very, very accessible. It just planes in R3. So so the model for H2 is your points in R2 with the y coordinate positive, and I will switch back and forth between points and complex numbers. And so these are the points, and then we have to get the metric. So this is called the upper half plane, and then there's the metric, the hyperbolic metric. So it's the Euclidean metric just scaled by the height. So what happens is that this is your upper half plane, but even though this looks in Euclidean distance at a finite distance from any given point, if you look at the hyperbolic metric, as you go down, your y goes to 0, and then the distance is going to infinity. So it's really a complete metric space, because this line is really not at finite distance. And once you have a geometry, again from Euclid's point of view, you have points and then you have lines. So the lines, and when you have a Riemannian metric and so on, these are called geodesics, and the lines, hyperbolic lines, are vertical lines and half circles. So with centers on x axis. So, here are your vertical lines and then here are your half circles. So, these are your lines. And you have points and lines, then you have angles. So, the metric also gives you a distance formula and it gives you angles. There is a distance formula which you can write down. I am not going to write the distance formula down because it is a little complicated, but it is not really, we do not really use the distance. Typically the calculations are done by taking some kind of maybe a line segment and moving it to a very simple situation. So, this is just one of the models of the hyperbolic plane. There are many other models as well, and depending on the situation you switch the models. So, the angles are same as E2. So, it is a conformal model because the angles are preserved. So, whatever, if you take some intersection, the angle between this is what you see in the Euclidean angle. So, this for example is at right angle. This is exactly at right angle even in hyperbolic metric. And you can see why the angles are same as Euclidean. This is just a scaled Euclidean metric. The Euclidean metric is dx squared plus dy squared, and you are just scaling it at every point. And scaling, which is just a similarity, does not change angles. So, hence the angles are preserved. The next thing is isometries. So, transformations which preserve the metric, and so here are some examples of isometries which you can very easily verify, because the metric, just by straight calculation and seeing that the metric is preserved. So, you can just do horizontal translations that will preserve the metric. You can also stretch it. Now, this is not a isometry for Euclidean plane, but this is a hyperbolic isometry. You have reflection. So, this is a reflection in the y axis, and by translating and translating back, you can have reflections in any vertical line. And reflections are very important because in the geometries, all E2, S2 and H2, reflections generate the isometric group. There is the famous 3 reflections theorem which we usually see in Euclidean case, but it actually holds true in the spherical geometry and hyperbolic geometry as well. And so, reflections generate the isometric group, and we are looking at the reflections in the y axis. The new component here is the reflection in the circle, which is called an inversion. So, the inversion is a reflection in a circle, and that looks like the one which I am giving you is 1 upon z bar, and this is a reflection in the unit circle. So, what it is doing is you take the center and then you draw a line from it, and a point over here will be taken to a point outside the circle at an inverse distance. So, this is very nice inversive geometry, and sometimes in a complex analysis course you see this this inversions in circles, and one of the theorems you prove is that inversions preserve generalized lines and generalized lines, and generalized lines is effectively a circle or a line, and they all are given by a very standard equation. So, this has consequences for hyperbolic geometry. It means that all of those transformations preserve lines, and the moment you start preserving lines, you can preserve distance. So, they all become isometries. So, really very pretty interaction between complex analysis and hyperbolic geometry. And so the isometric group of H2 is the group of Mobius transformations with coefficients in R. So you have A, B in R, and you have the determinant should be 1. So you recognize this as your group PSL to R, and these are Mobius transformations. Now, there are a couple more interesting objects which come up in hyperbolic geometry. Did I say something wrong? Oh, I'm sorry. Is that right? Oh, it's terrible. Yeah. Should we all leave? Right? Shouldn't we all leave? Is this a drill? Everyone is. See? Yeah.
It's probably too noisy to stay.
Stop.
All right. I should be more careful what I say. Yeah, you can come in.
You forgot the question by the
This is yeah. This is fine. Yeah. False alarm. False alarm. All is well. So, the couple of extra ingredients in hyperbolic geometry is the first one is what is called a circle at infinity. Now, if you look at the x axis, this is your x axis and this is the upper half plane. The geodesics which you see are actually ending at this circle at this line on the x axis. And so, points on the line, two distinct points will determine a unique geodesic. And so, unlike in R2, where if two lines are parallel, they kind of go on. They all go to the same point, infinity. But here, different things can happen. These two lines do not intersect, and they are going to different points. And so, you can make sense of this more rigorously by taking a compactification of H2 and seeing that the compactification is obtained by adding points which are topologically worth a circle. They're adding a circle. So, that's the circle at infinity. It's S1, which in this model looks like R union infinity, but there are other models like the Poincaré model where it's actually a disk. So, and we can is actually a circle. So, we think of this as the compactified hyperbolic space, and this is the circle at infinity, and it has very interesting properties. So, two distinct points on S1 determine unique geodesic any two geodesics either intersect in H2 or intersect on S1 or are parallel. So, here are two geodesics intersecting, and here are two geodesics which are intersecting at infinity or at the circle of infinity. And if you just extend this below, this is not H2, but if you just extend this, you see that this circle is just tangent. All you are getting is a tangency. And so the angles here are also very interesting. This is a 0 angle, and this angle is whatever the Euclidean angle is over here. So when you are intersecting at circle of infinity, you also have angle 0. The angle of intersection is 0. So that is one new object. The second new object is something Euclidean inside here. So you look at what are called horocycles. So a horocycle is centered at a point at infinity, centered at x belonging to this S1, the circle at infinity, is a curve perpendicular to all geodesics incident to x. So what is going on? Here are all geodesics incident to infinity, all the vertical lines. And now you are looking at a curve which is perpendicular to all vertical lines, which is a horizontal line. So this is a horizontal line, and so that's a horocycle. So this is perpendicular over here. Moreover, since this is a horizontal line, the y coordinate is fixed. So the metric here, the induced metric, is actually a scaled Euclidean metric, scaled E2 metric here, because it is some kind of dx squared plus dy squared divided by some constant because of the constant height. So you have a scaled Euclidean metric on this one. Yes. Yeah, but not to all geodesics. It's centered at x is a curve perpendicular to all geodesics which are incident to infinity. So what's a line which is perpendicular to all vertical lines, not just one vertical line? And so suppose, as I said, if x is infinity, this is a horizontal line, and if x belongs to R, then this is a circle which is tangent to the x axis. At this point x. So for example, if you have x here, this is what is a horocycle, centered at x. And similarly, if you look at the interior of the horocycle, is called a horodisk, is horocycle plus interior. We don't really need the stuff for H2. I am just writing this for S2 for H2 because it's slightly easier to draw, but we really need all of this for H3. So this would be like an horodisk. And the last part for hyperbolic plane are triangles. So you have triangles like you have in triangles in the Euclidean space, and what's interesting is that there's a famous, very nice computation shows you that the area of a hyperbolic triangle with angles alpha, beta and gamma is pi minus alpha plus beta plus gamma. In particular, the sum of the angles is less than pi, and that it's the difference is exactly the area. And this you can use this this formula for the area to also define and understand curvature and see that the curvature of hyperbolic space is negative or -1. So, there is a way to understand it using the area as well. It is the area defect. So, so that's one. There is another object called ideal triangle. An ideal triangle is a triangle with all vertices on S1. So, is this okay? Can you see here? So, here is a triangle which has all three vertices on the circle at infinity. That is an ideal triangle. So, as I was saying, that if you kind of try to do geometry, you have this boundary. There is a hole here, maybe you do not see it. There is a boundary over here. If you look at the interior of it and you want to put a geometry which is complete, you need to kind of have something infinite, but you also need to have finite area. So, this triangle is really going to infinity, but its area, well, we just saw what the angles are. This angle is 0, this angle is 0 and this angle is 0 here, because they are meeting at infinity. So, the area of this triangle is going to be only pi. So, this area is actually just pi. The other interesting part about ideal triangle is there is only one isometry class of it, because PSL to R acts triply transitively on the real line. So, PSL to R, this is one action on this S1 is triply transitive. Triply transitive means that it takes any 3 points to any other 3 points, and this implies that you can always take any ideal triangle and put it in the form 0, 1, infinity. And so, this implies that a unique isometry class of ideal triangles. Okay. Now, I am going to go through H3, but much faster, because we have already seen many of these ideas in H2. So, for H3, again we have the model, the upper half space model. And so, what is the model? You give points, you give lines, you give planes, you give isometries. So, you have H3 x y t with t positive, and similarly we think of this as complex numbers and t with z belonging to complex numbers and t positive. And again we have the metric, very similar, scaled by the height. So, we have the metric scaled by the height. And then we have the geodesic lines and then planes. So, geodesics are vertical lines and semicircles perpendicular to xy plane. and just one more, we have also the planes, and the planes are vertical half planes and hemispheres with center on xy plane. So, this is your model, and then these are your geodesics, and then these are your planes. So, your planes and lines. And we have isometries. So, let me just give you a very similar. You have horizontal translations, then you have dilations, you have some kind of rotations, which is everything is working out in just the z coordinate. So, but again you have in addition to the other ones which you saw before, you have inversion in sphere. This is your reflection isometry corresponding to the reflection, and this inversion in a sphere looks like this. And what it does is, it takes again the points inside the sphere, it takes them to outside, and from outside it brings them inside. It's really exactly like a reflection. And so the isometric group, which is generated by reflections, which are these inversions. Well, but I just want to show you the positively oriented, the orientation preserving isometries is the group of Mobius transformations. Now we can have complex coefficients. And this is PSL to C, and these are your full group of Mobius transformations. And there's really very interesting properties of Mobius transformations. And I remember when I was learning complex analysis in my MS in Bombay University, our professor did spend a long time on Mobius transformations. We had no clue why we were spending so much. These are just like fractional linear transformations, like. And then we saw all of these very interesting properties, preserving lines, planes, triple transitivity, this, that. We had just no clue why they are so interesting. I won't say that. Not while I am being recorded. Yes, it's a geodesic plane. So, like you have planes in E3, the hyperbolic planes are these hemispheres. And again we have the sphere at infinity. What I should say is, if you look at this group PSL to C, I have just shown you this actually is not an equality, it's actually an isomorphism, because this just acts on the complex plane, or actually the complex plane union infinity, and this action can be extended uniquely to an isometry inside H3. So, you have this sphere at infinity as before C union infinity, and your Mobius transformations act on C union infinity, and the action extends uniquely to an isometry of H3. this connection to Mobius transformations and this connection to the matrix group is very key to make this hyperbolic 3 space and hyperbolic 3 manifold theory completely different, and also the hyperbolic 2 manifold hyperbolic surfaces theory completely different, because you get the PSL to R and PSL to C, which are really interesting groups, very interesting properties. But this does not happen in higher dimensions. You can go through the whole thing with higher dimensions, Hn. I could have done the whole thing with Hn. All of these properties hold except the connection to the matrix group, the SL to C or SL to R. And so the hyperbolic geometry in higher dimensional manifolds is much is not that interesting. Various things, there is no sort of deformation theory, there is no convergence, and there is no the volume spectrum is not very interesting. So all kinds of things don't work, and this coincidence is can be traced to the fact that you can see the complex numbers and H3 in using Hamilton's quaternions, and there is the quaternion multiplication. You can change it and you can study that and see this as H3 action and H2 action and so on. So this coincidence with PSL is coming from the quaternion point of view, which we are not doing here. That you have to go through the hyperboloids and so on. Yes.
Extension holds the n dimension or not?
The extensions all work, yeah. The extension is fine, because then you don't have the Mobius transformations, you just have inversions in spheres. And so the inversive theory works, that is completely fine. The connection to SL and PSL doesn't work.
Inversion doesn't generate the Mobius group?
Was that? Yes, the Mobius group in n dimensions, but it is not isomorphic to PSL, say SLNC or something.
Or the Clifford numbers perhaps?
The Clifford algebras, that's a whole, I don't know anything about them. But the quaternions are the, but that you are looking at very different sort of only arithmetic manifolds and so on. Okay, I am almost out of time. Can I take maybe a few minutes more? So like we have triangles, we have tetrahedra, but now I just want to focus on ideal tetrahedra. So these are hyperbolic geodesic tetrahedra. So the faces are planes and it's all made up of lines and so on. Hyperbolic geodesic tetrahedra with all 4 vertices on C union infinity. So for example, so here is a hyperbolic ideal tetrahedron. And now what's interesting about this tetrahedron is you can now classify it and you can parameterize it. Now if you cut this with some did I not explain horospheres? Oh, sorry. I just need I'm sorry. I just need one more thing before ideal tetrahedron. Horosphere. Exactly the same idea. It's a surface which is perpendicular to all geodesics, passing through centered at x, passing through x. And what's interesting again is that it has a Euclidean metric, because it just scaled Euclidean. It has Euclidean metric scaled. This is a very important fact. We will need this later. If x is equal to infinity, this is again the horizontal plane, and if x belongs to C, then this is a sphere tangent to x and x. So what I am drawing here is, so if you cut this ideal tetrahedra, like just slice it, you get a Euclidean triangle. So, this is called link of a vertex, of a ideal vertex. So, this link of an ideal vertex is some triangle, but only well defined of the similarity class, because you can scale up and down, right. So, it can expand or it can contract. So, it is only well defined up to similarity class, and here is your ideal tetrahedron. And what you can do is, if you have a Euclidean triangle up to similarity, you can use Euclidean similarities to make it so that one vertex is at 0, another one at 1, and the last one is at z. So, what you get is a complex number which you can associate it to the tetrahedron determining its isometric class. So, what I want to point out is that the isometric classes of ideal tetrahedra is similarity classes of Euclidean triangles, and these are also again angles of a triangle, and this is parametrized by the upper half plane. So, it is parametrized by I do not want to say it is not one-to-one correspondence, because there is there is a choice of orientation and the order of vertices. So, depending on which vertex I put, there is a choice of this link, right. The way I have this link, I can put different vertices at 0, 1 and the remaining part. So, depending on which one I put, I actually get, so I can get z, or I can get z prime, or I can get z double prime, which looks like this. Moreover, if you look at this picture, this z over here, you can associate it to this edge 0 infinity, because when you see this picture, you are actually looking from a point at infinity down. So, you are looking at it down over here. So, this z here 0, 1, z and infinity. So, I am putting my vertices of my ideal tetrahedron at 0, 1, infinity and z. So, this z actually can be associated to this edge like so. And there are different choices. The way I send 4 vertices, there are 24 choices, the permutation group, and depending on the permutation group, there is a symmetry of the tetrahedron which is Klein 4. So, you actually get 6 choices, 3 of them are orientation reversing, so which we do not want those permutations, they are odd permutations. So, the even permutations leave you with z, z prime and z double prime. That is an order 3 transformation. And so, the way it looks is, this is a picture you will see in all hyperbolic 3 manifold stuff. You have z, z prime, z double prime, you are associating a complex number to every edge, and the opposite edges get the same because of the symmetry. So, that is your ideal tetrahedron and the edge of the ideal tetrahedron. So, this number z is called the edge parameter. And if you want, this is 0, infinity, 1 and z. That is how actually the vertices will look if you want to put them in complex numbers.
Why are you putting z? Is there z on the edges?
Yes, because when I look from above, I actually am seeing this triangle to 0, 1, z over here. It is associated to which vertex is going to 0 and which vertex is going to 1. So, this is, I am associating this z to the edge. The other interpretation is that multiplication by z is so let us fix this z naught. Multiplication by z naught is giving an isometry of the hyperbolic space, which takes this side to the other side. So, it is like a fan. So, it just takes this side to the other side like this. So, so tomorrow I will I have to stop because we have run out of time. But tomorrow I will continue with a little bit about volume of ideal tetrahedra, and then we will go to hyperbolic 3 manifolds. Thank you. Yeah, we can discuss more over the lunch break. I'll be happy to answer questions. You should ask lots of questions. Yes.
So you have associated this opposite edges like
Yes.
same ZZ. How is it related to this?
So there is z here. The opposite edge here is this is going to be z, and then this edge will get z prime because there's a right hand rule here, and this is going to be z double prime. So this is z prime. This is z double prime. So it's essential for what we are going to do tomorrow to see that every edge gets a z over here. Yeah. And you can think of this as the isometry which is obtained by multiplying by z is taking this face to the other face. It's taking the face 0 1 infinity to 0 z infinity, that transformation. It's also related to the cross ratio, but if I had tried writing down the formula for cross ratio, it would have taken another 5 minutes. So, this is, as I said, a very quick introduction, but I'll put up the references so you can read more about it.
The volume of the ideal tetrahedron is in terms of this z. That
It is given in terms of z. Easier formula is given in terms of the angles, which I will do tomorrow. That's the Lobachevsky functions which I want to see. The dilogarithm thing is using the z. Yeah, but I am not going to go to the dilogarithm. Again, writing the formula will take some time.
Yeah. But the Kashaev's invariant
Yes.
comes from that.
The Kashaev's invariant comes from the easier dilogarithm function. The volume of here is what is called the Bloch-Wigner dilogarithm, which is slightly more souped up because they want the function to be real analytic on c minus 0 1. So it needs to be souped up a little bit more to avoid the branch points. Thank you. Thank you.